This conference will now be recorded.
Hello everyone. Chemical properties of alcohols. This topic we have already started in last class. Today we will finish it, and after that there will be discussion related to application of different types of alcohols, mainly the simple alcohols, and then we will see how to distinguish 1 degree, 2 degree and 3 degree alcohols, and also related problems. Now for conversion of alcohol to aldehyde, that is oxidation process, what are the different types of oxidizing agents we use? That is both weak oxidizing agent as well as strong oxidizing agent. Now depending on our requirement, if we want to make aldehyde starting from 1 degree alcohol, then it should be used. What type of oxidizing agent should be used? Should be weak oxidizing agent. But if we want it ultimately up to carboxylic acid, then we have to use some strong reagent. So here we can see this 2 degree alcohol are using oxidizing agent. Now in this case, actually after conversion of this alcohol to the corresponding carbonyl, further oxidation is not possible because we have only one hydrogen. If you consider 1 degree, then there is a chance that first after the formation of aldehyde, as there are one more hydrogen, so further oxidation is also possible, but in this case that is not possible. Now here all these examples that you can see here, PCC, PGC, SWAN, DMP, all these are reagent, oxidizing agent obviously, which can stop the reaction at the aldehyde stage when it is primary alcohol. But if it is strong reagent that you can see here, now it will be directly converted to carboxylic acid. It will not be possible to stop the reaction at aldehyde stage. So this is for primary alcohol. But for 2 degree, just one oxidation is possible, which is as if removal of these two hydrogen. So finally you are getting C double bond O. And if it is 3 degree, now reaction is not at all possible. Now the reason is when it is 3 degree, the carbon with which OH is attached, that is also attached to 3 more carbon. So here we do not have any hydrogen attached to this carbon. So that is why removal of this hydrogen which is attached to oxygen and the hydrogen attached to carbon, that type of dehydrogenation is not possible. So for 3 degree alcohol, remember, you cannot oxidize it. Whatever is the nature of oxidizing agent, that is whether it is weak or strong, that is not important, but here oxidation itself is not possible. Now after oxidation, next we will see for chemical properties of alcohols. Number 4 reaction is catalytic dehydrogenation. Now when we are talking about this previous method, that is that we have just finished, oxidation of alcohol to aldehyde or ketone, that is also one type of dehydrogenation because ultimately you are removing two hydrogen atoms, fine. But in this case directly we mention the term catalytic dehydrogenation because now we will use some catalyst. So in presence of some metal catalyst, there will be removal of hydrogen. Now here what metal catalyst we use? We use heated copper, 573 Kelvin, very high temperature. When the vapors of primary or secondary alcohol pass over heated copper, maintaining this temperature, then dehydrogenation will take place, and depending on whether you have taken primary alcohol or secondary, either you can get aldehyde or ketone. So when it is primary, you will get aldehyde. If it is secondary, you will get ketone. But remember, if it is tertiary alcohol, now instead of dehydrogenation, now what takes place? Dehydration takes place, and ultimately you get elimination reaction, which is giving you alkene, that is CC double bond. Okay, so this type of reaction will take place because in tertiary alcohol, which is this one. So for tertiary alcohol here, as we do not have any hydrogen attached to this carbon, so that is why dehydrogenation is not possible even when it is catalytic dehydrogenation. So in this case, what will happen? OH and another hydrogen with respect to this OH, another hydrogen which is at beta position, that will be removed, and ultimately we will get CC double bond. Ethanol, which is 1 degree alcohol, in presence of this catalyst 573 Kelvin, we are getting aldehyde, that is acetaldehyde or ethanol. And if you have taken this 2 degree alcohol, this is 2 degree because this carbon is attached to 2 more carbon. Now we are getting ketone because it is 2 degree alcohol. So it is basically propanol, or you can also call it acetone. But remember, if it is 3 degree, as there is no hydrogen attached to this carbon, so what will happen now? With respect to OH, this carbon is alpha and all these carbons are beta. So there are basically total 9 beta hydrogen. So any of these beta hydrogen, because all these 9 hydrogens are basically equivalent, any of this beta hydrogen can be removed and ultimately there will be double bond between 2 carbon. So in this case, suppose the hydrogen is removed from here, so there will be CC double bond at this position. So ultimately what we will get? We will get alkene. Okay. So remember, when it is catalytic dehydrogenation, for 1 degree and 2 degree you are getting carbonyl group is generated, right? But in this case, that is 3 degree, as there is no hydrogen attached to the carbon with which OH is attached, so now we are getting completely different type of reaction, which is elimination. And how it is occurring? It is basically dehydration, because ultimately it is net removal of H and OH. So as if it is removal of water. So that is why the name we are using dehydration. One H from any of this methyl and OH. So it is net removal of H and OH, that means water removal. We have a question here. An organic compound which is X, on treatment with pyridinium chlorochromate. Pyridinium chlorochromate is PCC. So PCC is oxidizing agent. Basically, it is not very strong oxidizing agent. If you use this oxidizing agent with 1 degree alcohol, you will get aldehyde. So you have taken an organic compound which is X, you are treating it with PCC in CH2Cl2, which is nothing but solvent, and you are getting Y. So from X, you are getting Y. How? By some oxidation method. Now this oxidized product Y, it can react with iodine and NaOH. And what it forms? It forms iodoform. Iodoform is CHI3. So iodoform reaction is possible in some special cases if there is ketomethyl group, CH3CO, or CH3CHOH, this type of group. That must be present. Then only iodoform reaction is possible. Now it means in the compound Y, there must be CH3CO group or CH3CHOH group, right? Now if that is the case, that means Y is either ketone or aldehyde, or it may be alcohol also. Now as you are using PCC, that is oxidizing agent, with X, that means after oxidation you are getting Y. So there must be some carbonyl group, right? Now when you are using PCC and you are getting carbonyl, that means what will be the nature of X? Is it must be alcohol, right? So alcohol treated with PCC, that means oxidizing agent, you are getting some carbonyl compound, and that carbonyl compound is giving iodoform test. Now look at the options. Option A is only alcohol, right, which is ethanol, but molecule B, it is acetaldehyde. Molecule C is ketone, and molecule D is carboxylic acid. Now we have to find out the compound X, not Y. So X is alcohol. That means based on this information, we can say that the starting material is ethanol. This is Y. And in Y, as there is ketomethyl group, so that is why it is giving positive iodoform test, yellow precipitate of CHI. So just based on this information, that first X is oxidized in presence of PCC, we are getting carbonyl compound, and then this carbonyl compound is giving positive iodoform test. So the starting material must be alcohol. And Starting material cannot be aldehyde, because in aldehyde, if you are further treating it with PCC, suppose if this compound is X, you are treating it with PCC, further oxidation is not possible, because PCC can convert it only to aldehyde. Further reaction is not possible. If starting material X is CH3COCH3, then also in presence of PCC, further reaction not possible. And D, it is not possible at all. Fine. So correct option is this one. In this molecule, we have a compound cyclohexane system. There is OH. That means it is alcohol. Two methyl groups are also present at this carbon. In presence of H plus, we are getting P. We have to find the product P. Now, when in question specifically it is not mentioned that find the major product, obviously you have to consider, when nothing is mentioned, just consider it as if it is asking for major, because it may be that in the reaction that is given 2 to 3 compounds are produced, but you have to choose just one, so obviously it will be the major one. Now starting material, as there is OH, and reagent it is given only H plus. That means in presence of acidic condition, what will be the fate of OH? OH will be first protonated, and when it is protonated, it will be removed as water molecule. That means it is dehydration. When there is dehydration, there is carbocation formation, right? Now, when there is carbocation, next you have to check any rearrangement possible or not. So there may be rearrangement, there may not be rearrangement, depending on the nature of carbocation. But finally, what will happen? Finally, one H plus will be again removed, and the molecule will be neutral again, and there will be a CC double bond. That means, based on this information, you can understand that compound C cannot be correct option, because here you do not have any CC double bond. D also not possible, because again, see here OH is here, only the position of methyl is changed. So even if you consider that first there will be some carbocation formation, and then again to this carbocation, whatever is the position of methyl, to this carbocation, if you finally want to get OH, then there must be attack by water. Then only the final compound can be OH. But that is not possible, because in arrow in the question, no water is mentioned. So this is not possible. So option C, option D, both are not possible. Okay. Next thing is, if now we are left with A and B. Now among A and B, if you are considering option A molecule, position of methyl groups are fixed. It is not changed. That means no rearrangement is there. But if you are considering option B, there must be some rearrangement. Then that is the reason one of the methyl now changing its position. Okay. So first OH is protonated. It is converted to OH2 plus. Water will be removed. You are getting carbocation. Now this carbocation is 2 degree. Now rearrangement, is it possible? Yes, it is possible. What will happen? Now this one of the methyl group, it will be shifted at this position. We are calling it 1,2 methyl shift. Why? Because if you consider the position of this positive charge as 1, this carbon will be 2. So from 2 position it is going to the next position. So that is what is 1,2 methyl shift. After shifting, now as CC bond is broken at 2 position, there must be some positive charge. And look, this is 3 degree. So from through 2 degree, after methyl shift, you are getting 3 degree, and this is the reason why rearrangement is occurring. But finally, you have to remove one H plus, and that will be removed from this position. Now, if you are thinking why not from the left hand side position, I am talking about CH3, positive charge is here, another CH3. So what we are doing, we are removing this hydrogen. But if you are thinking that why not the other hydrogen? Now see, if you are removing this hydrogen, what type of alkene you will get? You will get this type of alkene. And if you are removing the right hand side hydrogen as it is mentioned in this box, now you will be getting this one. Now among these two alkene, that is I am talking about this option B molecule, and this is another possibility. Now among these two, obviously option B is more substituted alkene. Total 4 substituents are there, 2 methyl and these two side of the ring. So obviously B alkene is more stable. So that is why this hydrogen which is in the right hand side, this one, that will be removed, not the other one. Other one may also be removed, but that will give you minor product. But you have to write the major one. So option B is the correct option. After finishing chemical properties of alcohol, next we will see chemical properties of ethylene glycol. Now this is also alcohol, but we are discussing that topic separately. And the reason is in ethylene glycol you have more than one OH. Total two OH groups are there. So it's at and also at 1 and 2 position. So because of this particular that is more than one OH at 1 and 2 position, because of this feature, chemical properties will also be completely changed. So that is why we discuss separately, not in general reactions with alcohols. Ethylene glycol contain two primary alcoholic groups and it exhibit the usual reaction of hydroxyl group, but still there is some difference. Now if we consider other primary alcohols, because ethylene glycol is also primary alcohol. Here also you can see it reacts with metallic sodium and the H atom of OH group that is replaced by sodium. And as there are two OH group, so both the hydrogens can be removed or one of the hydrogens can be removed. So you can get monosodium compound or disodium compound. Now this hydroxyl group can also be converted to some halide group. If you are treating it with halic acid, that means halogen will be there. So halide will be coming from this halic acid. It will be at the position of OH. You can also use any of this phosphorus reagent or thionyl chloride. So this type of reaction we have already seen in case of alcohols. And as it is also one type of primary alcohol, so you can expect this type of reactions. But there are some other types of reactions also apart from this. So mainly we will discuss that because these reactions, as it is mentioned here, PCl5, PCl3, SOCl2, all this we have already seen. So that is also possible here. But what are the other possibilities that are not possible with normal alcohols where only one OH group is there? Mainly we will focus on that. First reaction is reaction with hydroiodic acid. When ethylene glycol is treated with HI or phosphorus in presence of iodine, what will happen? First, there will be formation of 1,2-diiodoethane. That means both the OH group will be replaced by iodine. But remember, that is not the end of the reaction. It is just intermediate. Finally, these two iodine together, it will be removed in the form of iodine. That means as if this carbon I bond is broken, CC double bond formed, and this carbon iodine bond is also broken. So finally, you are getting ethylene. But if it is simple primary alcohol where only one OH group, then it will be simply converted to the corresponding iodide. Further reaction not possible. But in this case, as two iodine atoms are present, adjacent position, that is 1 and 2 position. So obviously, further reaction is also possible. Second type of reaction, if it is reaction with nitric acid. Now, if you are heating ethylene glycol with concentrated HNO3 in presence of concentrated H2SO4 also, then there will be formation of dry nitroglycol. So OH group, now it is replaced by ONO2 group, and that is coming from HNO3. So this is, you can also write it as if it is NO3, but to, if you want to have proper idea that what type of bonds are present, here you can see as you, there is carbon oxygen bond, then oxygen nitrogen bond. So it is not that carbon is attached to nitrogen. No, it is not that. So that is why if you are writing this molecule in this way, that CH2NO3, it will be wrong. It is not the correct way to draw the molecule. It should be written in this CH2O then NO. So it is known as dinitroglycol, but IUPAC name will be 1,2-dinitroxyethene. Third reaction is dehydration. Ethylene glycol undergoes dehydration reaction under different conditions, and also it will yield different product. Now, normally when we say dehydration, mostly you have seen it in case of alcohols where we use some concentrated H2SO4. There is protonation of oxygen, and that is now it is converted to H2, and it is removal of water. But in this case, it is not acidic condition we are using. We are simply heating the ethylene glycol to a very high temperature, which is 773 Kelvin. And what happens? Here also water molecule is removed. So as if one OH, another H is removed, and you are getting carbon oxygen bond. And this is known as epoxide. Mainly this type of molecule, it is basically written in this way. You can call it epoxide, 1,2-epoxyethene, or oxidant. Another dehydration. If you are heating ethylene glycol with dilute H2SO4 or anhydrous ZnCl2 under pressure and in a seal tube, you have to maintain all these conditions. Now what is happening? First, water is removed. So as if it is removal of one H and OH. But remember, here epoxide is not formed, right? As if here this H and this OH, if you are removing it, then there will be CC double bond formation. Now this is known as, you can call it vinyl alcohol, because vinyl group is this one, CC double bond, then there is OH. So that is why the name vinyl alcohol, or you can call it ethanol. But remember, it is a type of enol, because enol means what? There will be CC double bond, and there is also OH group present adjacent position. Now why it is enol? Because it is in, CC double bond is in, right? And this is all. So together the name combined enol. So this type of structure, CC double bond adjacent to H, it is known as enol. And whenever there is enol, there is a chance of tautomerization. And in tautomerization, what happens? Now this double bond, one of the bond, it is now shifted here, and H will be going to methyl groups. Fine. So finally what we are getting? We are getting CC double bond. So if you are having trouble to understand it, I'm writing it here. CH double bond CH, and so now what is happening? This OH bond is broken and CC double bond is also broken. So as if now the position of H atom is changing. So now it is CH3, then C double bond 1H. So what you are getting? You are getting acetaldehyde from ethanol. Now it is converted to ketone. So it is known as ketoenol tautomerization. And you can also write the same molecule, that is acetaldehyde. You can also call it ethanol. Now it is written in this way. So if you are using this type of reagent, first there is removal of OH and H, you are getting CC double bond, and it is a enol type of structure, and enol will be finally converted to a ketone by ketoenol tautomerization. So ultimately our product is acetaldehyde when we are using this type of reagent. Now the third possibility, when distilled with concentrated H2SO4, glycol forms dioxide. So all these three boxes that you are seeing here, all are examples of dehydration. The difference is we are using different conditions, but ultimately it is removal of water. So you can keep it under dehydration category. When it is distilled with concentrated H2SO4, now we have taken two ethylene glycol molecule. So this is one molecule written linearly, then another molecule. Now as if it is removal of two water molecule, so one H and OH. this is another H and H. So from both sides, if there is removal of water, two water molecules, oxygen carbon bond will be formed, and this side also carbon oxygen bond. So there are total 4 carbon and 2 oxygen. So it will be 6-member ring, and the relative position of the 2 oxygen, it is at 1 and 4 position. 1, 2, 3, 4. So that is why the name is 1,4-dioxane. So this type of system, you can also write it in this way. It is known as dioxane. And suppose if I am writing it, placing both the hydrogen side by side, it is 1,2-dioxane. But dioxane means there will be cyclohexane ring, and 2 carbon of the carbon atoms of the cyclohexane ring, that will be oxygen. That is known as dioxane. But this is 1,2-dioxane because position of oxygen matters. So in this way, when you are distilling ethylene glycol with concentrated H2SO4, there will be formation of dioxane molecule, which is a type of cyclic ether. Number 4 reaction is oxidation reaction. On oxidation, glycol can give a variety of products, and that depends on what kind of oxidizing agents and other reaction conditions are maintained during the reaction. If it is HNO3 or alkaline KMnO4, they are basically oxidizing agent, then this type of reactions are possible. Now see, variety of possibilities are there. You have taken ethylene glycol, there are 2 H group. So suppose if one of the H group is converted to carbonyl group, it will be CHO, another part is intact. Now if another part is also oxidized, now 2-aldehyde, and this is known as glyoxal. There is another possibility, if keeping this part constant, you are oxidizing it further, then CHO is converted to CO2H, and this is known as glycolic acid. Then CO2H, keeping it fixed, CH2H can be oxidized to CHO, and finally CHO is also oxidized to CO2H, and there are total 2 CO2H. In this way, if you oxidize glyoxal further, then first, as if the one CHO is converted to CO2H, then another CHO is also converted to CHO. But final product what we are getting after all this oxidation, it is oxalic acid. When ethylene glycol is treated with HiO4, which is another oxidizing agent, final product is formaldehyde. That means H2CO. Now this reaction is selective for vicinal 1,2-diol. Vicinal means the position of 2 OH group, it will be at 1 and 2. And it proceeds to cyclic par iodate ester intermediate. So we are using ethylene glycol and HiO4 is the reagent. Now HiO4, it is basically containing iO4 minus. Now iO4 minus, if you want to know the oxidation state of iodine, it is actually, how we will decide? Total 4 oxygen atom, par oxygen minus 2 charge, 4 oxygen means minus 8. Now excess negative charge, if you write it in this way, excess negative charge is minus 1, and total negative charge coming from oxygen is minus 8. That means oxidation state of iodine is plus 7. Similarly, the final, that is the fate of HiO4 is after oxidation. Now it will be reduced to HiO3. HiO3 means it is nothing but IO3 minus, and here oxidation state is plus 5. Same way you can, as you have followed in case of IO4 minus, that is how you have obtained the plus 7 oxidation state. Same method you can also follow here. So IO4 minus is converted to IO3 minus, right? Now from plus 7, now it is changing to plus 5. That means it is reduction. Reduction of HiO4. That means it is oxidation of ethylene glycol. First, there is formation of this type of cyclic par iodate ester. So this CH2O and CH2O, this part is coming from CH2 is CH2H. And see here what we have, this portion, it is HiO3. So one oxygen is less, That means these two H and one oxygen from HiO4, if you remove in the form of water, this type of cyclic ester you will get. But this is not final product. Finally, what will happen? Now this CC bond will be broken. This CO bond will be formed. So you are getting one formaldehyde from here. Oxygen iodine bond is broken. This oxygen iodine bond is also broken. Another CO bond formed. You are getting another formaldehyde. And from this part, you are getting HiO3. Okay. So when you have taken 1 mole of ethylene glycol, 1 mole HiO4, finally you are getting 2 moles of formaldehyde, 1 mole of HiO3. Nitration of glycerol. Now we have finished chemical properties of ethylene glycol. Next alcohol molecule is glycerol. Now this is very interesting because now you have total 3 OH group. In the previous one you have seen 2 OH group at 1 and 2 position, but now 3 OH group at 1, 2 and 3 positions. So this is glycerol, the simplest example for this trihydroxy type of molecule. It reacts with concentrated nitric acid in presence of concentrated H2SO4 and ultimately it forms TNG, nitroglycerin. Fine. So here we have taken HNO3, it is written in a different way, but it is HNO3, then concentrated H2SO4. So all this H as if it is replaced by NO2. And this NO2 you can see from the color, it is coming from here. Fine. Dehydration of glycerol, that means water molecule will be removed. When you are heating glycerol with dehydrating agents such as concentrated H2SO4, KHSO4, now KHSO4 as if it is derivative of H2SO4, just remove one H of H2SO4 and replace it with potassium, it will be KHSO4. It undergoes dehydration and it forms acrolein. So here we have written KHSO4 and this molecule which is basically prop to enal. Why it is prop? Because total number of carbon is 3 and numbering will be started from this because it is carbonyl carbon, then 2, then 3. So at 2 position you have double bond. So that is why prop, because longest chain is 3 carbon. Then 2 position you have in, that is CC double bond, but you have to end the name with the suffix al because it is alkyl. So prop to enal acrolein. You can also write the molecule CH2 double bond CH, CHO. Or you can write it like this. So different way you can write the same molecule. And you should practice it also, because if you are habituated, suppose right now you are seeing this PPT and here the molecule is drawn as in a vertical position. But in exam it may be given in a different orientation. It may be drawn in any of these format, right? So it is actually same molecule, but you can draw it in different way. So when it is dehydration, final product is acrolein. But remember, dehydrating agent is either concentrated H2SO4 or KHSO4. Oxidation. So we have seen nitration, dehydration. Here also you have seen some oxidation. But this is for ethylene glycol. And this slide, ethylene glycol is finished. After that, we have started glycerol. First reaction, nitration. After the dehydration, now the third one is oxidation. Now here we have variety of oxidizing agents because depending on what type of oxidizing agents you are using, products will also be different. Now, as there are total 3 OH groups, so different possibilities are there. You have also seen in case of ethylene glycol, there are different possibilities, but now as one OH is increased, possibilities are also increased. When it is dilute HNO3, nitric acid, you will get from glycerol mixture of glyceric acid and tartronic acid. So you can see this is glyceric acid where 2 OH group intact only the last CH2H is converted to CO2H. And what is tartronic acid? The middle OH is intact, but the two terminal CH2H group converted to CO2OH. Okay. If it is concentrated HNO3, you will get only glyceric acid. If it is bismuth nitrate, you are getting meso-oxalic acid. See, this is the structure of meso-oxalic acid, where terminal CH2OH converted to CO2OH, middle CHOH is converted to C double bond O. If the oxidizing agent is bromine water or NaOBr, which is also known as Fenton's reagent. Okay, sorry, this is not known as Fenton's reagent. BrH2O, bromine water, or NaOBr, or mixture of these two compounds, ferrous sulfate and hydrogen peroxide, which is known as Fenton's reagent. If you use any of these three reagents, you will get mixture of glyceraldehyde and dihydroxyacetone. So what is glyceraldehyde? Glyceraldehyde is this one. Where see, two OH group intact, one terminal CH2H is converted to aldehyde. This is glyceraldehyde. So that is why the name is ending with aldehyde. And you will also get dihydroxyacetone. Now from the name you can understand. Acetone is CH3, COCH3. Just replace two hydrogen atoms from two terminal ethyl groups with OH group. Now you will get CH2H both sides. So that is why the name dihydroxyacetone. So when you are using any of these three reagents, you are getting mixture of glyceraldehyde and dihydroxyacetone. That is these two molecules. Their mixture you will get. And this mixture, it has a specific name which is known as glycerol. You may go question in this format that what are the reagents that are required to obtain glycerol starting from glycerol. So if in options, obviously any of these three reagents must be present. And if it is a multiple correct choice, maybe two or all these three reagents will be mentioned. So this mixture, that is known as glycerol. If oxidizing agent is HiO4 or lead tetraacetate, PbOAc whole 4, you will get mixture of formaldehyde and formic acid. Now this is simple structure. Formic acid is this one, HCO2H, and formaldehyde is this one. Okay. If it is acidified KMnO4, now glycerol will be converted to oxalic acid. So this one is oxalic acid. Oxalic acid. Fine. So here how many different types of reagents we have used? Dilute HNO3, then concentrated HNO3, then bismuth nitrate, then the fourth one, any of these three reagent, same mixture you are getting, number 5, and this is number 6. Okay, so these are the possible oxidation reactions that you can get from glycerol. Ethylene glycol mixed with oxalic acid, heated at 210 degrees centigrade. What is the major product? Now, what is the structure of oxalic acid? It is CO2H, that is COOH, then another COOH. And what you have taken? You have taken ethylene glycol. You are simply heating it. So this is basically primary alcohol plus carboxylic acid. But that is unusual thing is here you have two OH group in the same molecule, two CO2H group in the same molecule. So it is possible that you can first think that as if two water molecules can be removed and you can get a cyclic type of structure, right? Just we see in case of ester formation where you have one carboxylic group and one OH group. So same type of cyclic structure you can expect here as if removal of H, OH, H and OH. So now this oxygen carbon bond formed, this oxygen carbon bond. So this type of cyclic ester you can get, but this is not the end structure. And also see, any of these options, if you look, there is no cyclic product. That means this cyclic structure, it must be broken, it will be decomposed. And how that will happen? As you are heating it at very high temperature, CO2 molecule will be removed. So this is decarboxylation, minus 2 CO2. And from this part, what you are getting? Ethylene. So it is matching with this one. Okay. Acrolein is formed when glycerol is heated with which of these reagent? Now, glycerol, remember here HNO3, it is oxidizing agent, KHSO4, oxidizing agent, bromine water, oxidizing agent, acidified KMnO4, that is also oxidizing agent. And glycerol means there are total 3 OH group. And acrolein, we have just discussed in 2 to 3 slides, previous slide. I mean, if you move in the previous slide, 2 to 3 slides before, we have heard this name, right? Acrolein. So acrolein is basically CC double bond, then COH. Now, what reagent will give you this one? We have discussed that is oxidation of glycerol. Remember in this slide, right? So here, when we have used acidified KMnO4, the last point, number 6 point, you are getting oxalic acid. When it is bromine water, you are getting mixture of glyceraldehyde and dihydroxyacetone. When you are HNO3, you are getting glyceric acid or tartanic acid. But in none of these options, that is, in none of these points, you are seeing any acrolein molecule, right? So only one reagent is left. And also see, here in presence of KHSO4, this type of acrolein molecule is actually formed. So this is basically dehydration, because dehydration you can see, and as well as there is oxidation also. So one OH, that is, if you are considering this CH2H group and this CHO, it seems as if it is oxidation. But actually what is happening, this OH and this H, if you remove, there will be a CC bond formation, right? And if this H and this H is removed, now there will be C double bond O formation. So both type of reactions are actually occurring, dehydration as well as oxidation, right? So dehydration in this part, oxidation in this part. But we have discussed this under dehydration category. Okay. So in this question, the correct option will be KHSO4, because when you are using any of these 3 oxidizing agent, you are getting oxidized product. But when it is KHSO4, first what will happen? One OH and H will be removed, and there will be CC double bond, and CH2H, that will also be removed. Fine. So directly, if you consider conversion of glycerol to acrolein, as if it is removal of 2 OH group and then oxidation of CH2H. But remember, as we are calling it dehydration, so basically what will happen? First, there is removal of H and OH. That means removal of water molecule, and also this H and OH. So as if you are getting 2 CC double. Now this type of structure, as if you are writing it in this way, it will be easily you can understand. This part is actually enol. This part is actually enol. So there will be ketoenol tautomerization. This part will be intact. There is no change. But this part, as there is ketoenol tautomerization, so ultimately it will be H2C double bond CH C double bond OH. So this is the structure of acrolein. So though at a first glance it seems as if it is oxidation reaction, but actually if you consider this unstable intermediate, this is the actual dehydration product. It is as if removal of 2 water molecules. Okay, so 2 water molecules are removed. You are getting 2 CC double bond, but 1 CC double bond and together with this OH, it is actually enol. So ketoenol tautomerization will take place and it will be converted to aldehyde, and this is known as alcohol. So KHSO4 is the correct option. Here we have this beta ketoester. Why I am calling it beta ketoester? CO2 ET group. This is ester. With respect to this group, this is alpha position, this is beta. So at beta position you have carbonyl group. So that is why the name beta ketoester. In presence of ethylene glycol, A is the major product. But what is A? 4 different structures are given. Now in this molecule, we have 2 different types of carbonyl. One is ketocarbonyl, another one is ester carbonyl. Now among these 2 carbonyl, which carbonyl group, that is which carbon of these 2 carbonyl group is more electropositive? It is obviously the carbonyl group which is coming from ketone, not ester. Because when it is ketone, there is this type of resonance is not possible. See, when it is ester, lone pair of oxygen, it can take part in resonance. So after resonance, the double bond character of carbon oxygen bond, that is lost. But this type of resonance is not possible in ketone because there is no donating group. I mean, Placer effect is not possible, but Placer effect is possible in ester. So that is why if I am numbering, this is carbonyl number 1, this is carbonyl number 2. One is more electropositive in nature, and that is the reason if there is any nucleophile, it will prefer to attack at one carbonyl carbon, not the other one. Fine. Now when it is attack of any nucleophile, so here the nucleophile is basically ethylene glycol. In presence of H plus, what will happen? Look at this mechanism. In this mechanism, only with keto group it is shown, just omitting the ester part. Because we are not interested in the ester part, we will just see how the nucleophile is reacting with carbonyl carbon in presence of H plus. And the nucleophile is ethylene glycol. So first there is protonation of this oxygen. It is positively charged, and this is ethylene glycol molecule, which is our nucleophile. So it is attacking at this electropositive carbon, and this oxygen is positively charged. If this hydrogen is removed, now though details are not required, but if you are interested to understand how we are getting this type of dioxolate, that is cyclic ether type of molecule, then you have to check this mechanism. Fine. And in this way, finally we are getting this type of cyclic structure. Now in our case, as there is also ester group, so only this type of dioxolate that will form in the left hand side, the other part will remain intact. Okay, so that is why only in the left hand side part, in presence of H plus, you can also write it as if it is removal of 2 OH and 1 oxygen, and finally you are getting oxygen carbon bond both sides. So this type of structure, but this part is there is no change. So this is still as it is. So it is matching with which option? It is matching with option 2, right? But if you look at the other options, here option 1, if you look carefully, this is actually matching with this one. But this is actually intermediate, because whenever there is H plus present, the reaction will not stop at this point. This is option 1 molecule. That is analog of option 1 because it is completely separate molecule in this particular mechanism. So OH will be another OH, that is I am talking about this OH. That will again be protonated. Again this carbon oxygen bond will be broken. And finally, what will happen? There will be, see, this lone pair, it is again making CO double bond, and ultimately this H2O is removed, but another which it is attacking as nucleophile. So that is the reason this is not the end product. This is just the intermediate. So option 1 is not correct. Then option 3 is obviously not correct because we do not have any dioxylane type of structure. And option 4 is also not correct because here ester group is converted to carboxylic acid. But that is possible only when there is hydrolysis. Hydrolysis means there should be H plus, there should be water. But in the arrow, it is mentioned only H plus. We are not using any water. So ester group should remain intact. So that is why option 2 is the correct option. Uses of different types of alcohols, though mostly we will see uses of the primary initial members. That is 1 carbon alcohol, 2 carbon alcohol, ethanol, methanol, like this. So uses of methanol, it is used as a solvent for paints, varnishes, etc. Then as an additive in petrol, so that combustion is improved, because when petrol is undergoing combustion, we get energy. It can be used as a fuel in several internal combustion engine. Then manufacture of dyes, drugs, perfume, formaldehyde, that is for large scale preparation of all these molecules. And also very important application, it is also mixed with in very small amount to ethanol, so that we can discourage the overconsumption of alcohol, because only ethanol is consumed, not methanol. It has poisonous effect. So that is why if we want to discourage the consumption of ethanol, we have to mix some poisonous alcohol. So that is why this is another application. Uses of glycerol, remember 3 OH groups are present: CH2H, CHOH, CH2H. It is used as sweetening agent in confectionery beverages, manufacture of cosmetics, transparent soaps, printing ink, stamp pad ink, lubricant for watches, clothes. Manufacture of explosive like dynamite, cordite, when it is mixing with China clay. Ethanol, that is ethyl alcohol. Now it has very versatile application for preparation of paints, varnishes, and other organic compounds like this, etc. That is large scale manufacturing process for all these molecules. Ethanol is used. It also has antibacterial properties because it slows and stops the growth of microorganisms, and that is the reason it is used in hand sanitizer. Used as a solvent in laboratory because many organic compounds are soluble in ethanol, which are insoluble in water. So suppose when we are talking about organic compounds, mostly it will be water insoluble. Now, if it is water insoluble, but still you want to use some polar solvent, then ethanol you can use, because it is in that is, it will help to for solubility of all these organic compounds. It is good, and also there is some polar nature in it. So as if it is serving the purpose of solvent and also the polarity of water, but water you cannot use, but still this polarity you can expect from ethanol, though not so polar like water, but still some polarity is there. So that is why it can be used as a solvent to dissolve many organic compounds. Perfume, cosmetics, paints, detergents, inks, preparation of all these possible from ethanol, and sometimes it is used as the main component also. Fine. It acts as clean fuel because it undergoes complete combustion, and as a preservative for biological specimen in biology laboratory. Fine. And ethylene glycol, that is CH2H, CH2H, used as antifreeze in automobile radiator. Its dinitrate is used as an explosive with change. So these are the applications of these 4 alcohols. Distinction test of primary alcohol, secondary alcohol, and tertiary alcohol. There are, this is not the only reaction by which you can distinguish, some other test is also there. So this is the number 1, Victor-Meyer's test. It is a series of reactions. So this is not very simple test. There are actually the test is simple. If you performing it in laboratory, there is easy visual appearance. You can easily identify. The test itself is not difficult, but there is a steps involved. 3 to 4 steps are involved. So from that point of view, there is a series of reactions. So here what happens, different alcohol, that is from 1 degree you will get red color, from secondary you will get blue, and from tertiary you will not get any color. So the reagents that are used, first phosphorus and iodine, second reagent in the second step AgNO2, the third step HNO2, but HNO2 directly never used, it is always the mixture of NaNO2 and HCl that is used. Fourth reagent KOH. So total 4 reagents we are using one by one. Now see what are the reactions actually happening. When it is primary, that is RCH2H, general alcohol. Then secondary R2CHOH and tertiary R3COH. When the first reagent is used, it is very simple, which is converted to I. So in all cases you are getting iodoalkane. So this is number one step. Second reagent you are using silver nitrate AgNO2. Now iodine is converted to NO2 in each cases. So all are behaving in a similar way. All are nitroalkane. The third reagent HNO2. Now what is happening? HNO2. Here you have 2 hydrogen, right? So these 2 hydrogen and 1 oxygen from HNO2, if it is removed, you can get this type of nitric acid. In case of nitroalkane, there is only 1 H. In case of secondary. So as if in HNO2, if you remove this hydrogen and 1 H and 1 oxygen, so what will be left? NO will be left. So you are getting pseudonitrile. And in case of R3CNO2, there is no hydrogen, so no reaction possible. So up to this step, all are behaving in a similar way, but now you can see the difference. And finally, when you are using the fourth reagent, KOH, this nitric acid it will give you some red color. Pseudonitrile will give you blue color, and there is no reaction, so no color will be generated. So in this way, from the that is all these 3 are completely different, giving different color, and the last one there is no color. So you can easily understand which one is primary, which one secondary, and tertiary. So whenever you are doing any distinction test, there must be some visual change. It may be color change, it may be precipitate formation, it may be appearance of some dash with a specific smell. So there must be some visual change or any change that you can easily identify. So that's why this type of tests are used for identification or distinction test, so that you can understand it very quickly. Okay, so this is the first test by which you can differentiate these 3 types of alcohols. Next day we'll see another test also. So this the end slide. We end the session here. Thank you for listening.